Hey, what was I doing before? Oh yeah, so this I'm gonna go through bioplastics today and tomorrow, today and Thursday. Mostly it's like this well, there's a Nature Review paper that's pretty good. And then mostly it's from this the book Plastics in the Circular Economy, chapter 3, which is a really long chapter. So the guy that wrote that book is a bioplastics person, so most of the book is that chapter. Anyways, there's a lot in that. And then I've been kind of basing it on that and then taking off and finding things on the internet linked to it. Like there's some links here. I don't know. So I'll go through some other things. I'm going to add more to it before Thursday probably, and then we should get a pretty good coverage of this. And then let's see. I'm going to download that. Hopefully that works. Did that do it? Yes. And then so I got one more speaker. This this she got a master's in DAP and fast fashion on the plastics problem in fast fashion. So like exactly the stuff. So anyway, so we got a lot of speakers coming up too. We got like this week is bioplastics and Robin McNiernan from Procter and Gamble's the head of the like their circular plastic, circular economy effort. So she runs a pretty big group and then two people from Sun Chemical to talk about pigments, like circular economy for pigments and plastics. Then the Scott Trinor, who's like part of this plastics recycling organization that has all different companies involved in it. Hard to tell what's going to happen with that, but like kind of like what his function is, how those organizations come to play. Then one more, this Shelby Schaefer, who she's the one from DAP that did a master's degree in recyclable and fast fashion stuff. So hopefully, anyway, so the only way these things really, I'm telling all these people to just come in for a discussion. Like, so basically, it would be good if you guys like glance before you show up, maybe look at the web page or whatever for the company or whatever you can get. And then just think about having one question. Because if there's like 40 people, 40 questions will take up like 18 hours or something. I mean, so, and then just nailing them with questions is good. And if the more probing they are, the better. So, I mean, if you have some with companies or something, like just bring it up. Or if you agree or whatever, like your opinion is good. And then just kind of what they're doing. I think that we can get a lot out of it if we do that right. Otherwise, I can just talk to them like an interview, like too, but that's probably less, I don't know if that's as functional. And if you have a question, like I'm not really looking at the audience, so just shout it out. Like just interrupt. Don't, because it's just a discussion, so just say whatever you want. And if you raise your hand or something, I'll say, but basically, if I don't see it, just shout. Hopefully that'll work. I mean, I think it'll be a lot more interesting and engaging, and you can get something out of it. And also, like all these places are potential places to work, not the DAP person, but the other places, every place we've had, you can apply for jobs at these places, if it looks interesting. Like Ahmed can definitely give people jobs. Yeah, that was here on Thursday. I think all these people can. So if you part of it is like giving them an impression about UC too, like the P&G people, we kind of want them to think like we're like thinking on our feet and whatever, aggressive, asking questions, interested in stuff. So the more, I mean, it's part of it is impression for UC is good. And then also you can talk to them after, like Robin will be here, the Sun people, one of them will be here. Scott's online, and then Shelby will be here. So it's like split here and not here, but all right, hopefully that'll be good. Um, anyway, it gives me like the first time around, I'm kind of putting the class together. I have a framework and I have some materials, but kind of still like you can't do it in advance exactly. So I'm kind of framing up the class. So it's a little bit like first time around. That's how it goes. Any comments or anything, on that stuff? All right, so let's see. Where did my thing go? Oops, that was pretty good. No, I want to go to this. All right. So, yeah, bioplastics, let's see, get rid of this somehow. Want to go. Worried if I do that, it'll stop recording. Why is it that thing shows up when I don't want it and it's not there when I want it? Anyway, I hope it's okay. Anyway, so maybe you've seen, like this is PLA, polylactic acid, and then this is PHB, the kind of yellowish, looks like polyethylene somewhat. So those are the two most prominent bioplastics that you're going to run into right now. So, and people say like, so PLA is also what you use for uh, printing, 3D printing, it's the most common because it's like the most shape retaining or whatever plastic. As if you want to have a very sharp features, this is the plastic to use. I'm not sure why that is, but basically it is. And also it's quote unquote compostable, right? So it's not really, so if you put it in your backyard, it'll last longer than polyethylene. So you have to put it into a high temperature, high pressure machine that's going to industrially compost it. But at the same time, you can industrially compost a lot of things, like polystyrene. You can stick a lot of things into an industrial composter and they'll break down somewhat. So basically, it's got a bio source. So you can say, well, that means that like things that it's pretty easy to have flim flam in this operation. That's one part of it, right? So these are PHB. So PHB you can make into kind of a foam, you can make it into cups, you can make it injection, you can injection mold it into little platters, you can make forks and things with it. You can make film with PHB and PLA, you can kind of do the same stuff if depending on what you want to do. So kind of the two things. So then there's this whole realm of like so you can take corn ethanol and then from that, you can strip off the water and make ethylene from it. And then you can make polyethylene from that. So it's called a biosourced um, or bio-based plastic. So you can have polyethylene, it's just the same. You can by mass balance economy, you can have cuts of bio-based ethylene with petrochemical ethylene mixed. So it could be a 50% bio-based polyethylene. It's exactly the same as any other polyethylene, or it could be 80% or 10%, right? So that would be a biopolymer, even though it's polyethylene. Same with PET. You can make it into ethylene glycol, which is ethylene with two hydroxyls on the end, and then react it with terephthalic acid and make PET. So you can make a water bottle from kind of corn ethanol. That's what this picture is. And you make a polyethylene cap from the same thing, or you can make a polypropylene cap. So there's chemical processes to do that stuff, and they're going on right now. So there's problems with that, like you eat corn and you're also making plastic with corn. It's like there's a competition between your plate and what your plate is made of, like what your food is and what the stuff is on it. So that's not exactly a great situation to be in where like a chunk of the world is starving to death and you're making plastic with food, So there's this kind of issue about whether that's a good idea or not. Anyway, so you can also take waste wood and waste whatever, like the stalks and the cobs and things from the corn. And it's possible to ferment that into ethanol. This is like generation one bio-based uh, chemicals is ethanol from corn or from sugarcane. And generation two is taking the waste agricultural products or just wood chips, things like that, then fermenting that and making ethanol. So that generation one is well set up because it's a fuel cut, right? It's a biofuel cut that's common. Generation two is been around for 20 years, but it's kind of only now like being industrialized. It's still like, so in the government, they have SBIR, uh, small business initiation, something grants. Like in every federal agency has to give like 20% of their money to these, like any money they're giving out for grants, they take the total and they cut off like 20% has to go to these business startups. And you can apply for that. Anybody can get that money, right? So, and then there's phase one, phase two, phase three. Phase one is like a small amount to start the business. Phase two is like commercialization. Phase three is like a smaller amount to kind of get your feet on the ground after you've already done pilot plants and started commercializing. Right. So phase one's easy to get, phase two is hard to get, and phase three is kind of given if you got a phase two. That's more or less. So there's a lot of these generation two biochemical fermentation operations that are running on phase two SBIR from either Department of Energy, National Science Foundation, the NIST, National Institute of Standards Technology, and some of it's coming from the DoD, like the Air Force and whoever. And so there's a lot of this is supported. So I'll show you a couple companies like that they're supported by the government, but they're still kind of functionally doing it. Right. So there's a little bit of question of if this is how things are going, like how the whole operation works. Like in other words, it isn't like all of a sudden you're going to start a waste agricultural waste operation to make chemicals that will make polyethylene or something. It's the whole thing is kind of government influenced. More, there isn't a private enterprise exactly doing that on their own, put it that way. All right, so that's one. So there's a quadrant here. So one is just plastics from fossil fuels. That's our friendly and happy plastic world that's led to the problem we're dealing with. And then bio-based is this business of taking corn ethanol and making PET from it. And then that can be this mass balance economy, however much fraction cut you want from it. And three are actual bioplastics, which are PHB and PLA, more or less, right? So basically, and then these can be so bioplastics, if you make polyethylene, it's a bioplastic, but it's not biodegradable, right? And then PET and PLA are nominally bioplastics that are biodegradable. And there's also conventional plastics that are biodegradable. So you can make from fossil fuels plastics that will biodegrade, right? So that this leads to kind of a confusing situation, especially if you look at like, how are you going to label these things so that people know? I mean, people don't even know that those things exist. It's basically somehow a consumer is going to have to understand the thing they're buying, is it good for the environment or not? It's not a simple answer, right? It could be 80% good for the environment and 20% not. It could be a cut, or it could be, it's good in the sense that you're using plants to make it, but it's not good in the sense that you're not addressing the plastic waste problem at all. Right. So it isn't such a simple situation to say bioplastics are great. So anyway, the ideal, I guess, would be to have like number three, where you're both biodegradable and bio-based, and then you could get rid of the oil component of the whole thing, and the greenhouse gas issue would go away, kind of. And then your solid waste issue would go away. So three could potentially solve all problems. The problem is that there is a fossil component to making bioplastics, so it isn't CO2 free, right? And if you look at the table, the CO2 component of the bioplastic can be higher than the conventional plastics. So you're actually working backwards sometimes to make, so it isn't so clear cut that this is exactly the right route to take, right? And also economically, the stuff costs more. I think in all cases, it costs more, like 3 times as much. On the other hand, the plastic part of something you buy, the cost of the plastic isn't, so it's like the labor to make the textiles, you know, if they're paying people $1 a day and you're paying $30 for the shirt, like that $1 a day is not, if they tripled the price that they pay that person, it wouldn't influence the price of your $30 shirt. It'd be like 10 cents more. Like it's not even the tax. So basically, same here, like the plastic, such small amount of the plastic engineered, so there's such a small amount of material in the pieces that there's almost no plastic in it. So if you triple the cost of the plastic, that isn't really the cost of the thing. It's all markup, or it's all like designing the bottle the right shape, or the color of the bottle or whatever. You know, so it isn't, the plastic isn't necessarily a number one. Price of the plastic isn't that important. It's important if it's $10 versus 50 cents a pound. But it's not important if it's 50 cents or $1.50. It might not make any difference for some applications. So that said, so I made a list of like what, like if you wanted an ideal bioplastic, so you'd want 100% of the properties for the material. It would degrade immediately once you reach the designed lifetime. And then it would totally degrade into oxygen and nitrogen. That would be exactly what you'd want. Right. So there's some time span for degradation, like 90 days in a normal compost for polyhydroxybutyrate, and then like a little bit longer under different conditions. PLA in a normal backyard composter will never degrade. Like polyethylene will degrade first. And then if you put it in industrial, it's like 90 days again. So you have to have this high pressure, high temperature to degrade it, which you can also degrade PET. PET is essentially as degradable as PLA, right? Even though you say PLA is a biopolymer and PET is like the worst nightmare on earth, right? So, I mean, all right, the degradation product is lactic acid, which is a biomaterial, and the other one is terephthalic acid, which is carcinogen. So there is some difference between the two, but basically in terms of degradation. Anyway, so this would be like the design, if you wanted to think like, maybe you would have your own ideas, but this is what I came up with. So have non-toxics and no terephthalic acid, no phosgene, like polycarbonate degrades into phosgene, which is a nerve gas. That's like, I mean, that's what they use as a nerve gas. So basically, anyway, so like the largest deposit of nerve gas is like 80 miles south of here in Kentucky. There's a place where they have a big army base full of nerve gas. That came to my mind just now, so I thought I'd say it anyway. That's the wave, I guess, right? So anyway, so you want to have like non-toxic and also non-eutrophic, so it doesn't like contribute to the algae growth in Lake Erie. Like it could degrade and then just suddenly make all this phosphorus that all of a sudden Lake Erie's dead, right? Because of the eutrophication. So bioplastic degrading isn't necessarily a good thing in the wrong situation. If you're using it as a fertilizer, maybe that's good. If you're dumping it into a lake or ocean, it isn't good. You know, so anyway, so what it degrades into is an important question. And then the cost is important. So I said like 2 to 3 times is what we're at now. If you can make it cheaper than petrochemicals, then all of a sudden you might have the problem solved. Like cost could be the whole thing. And then you want to have it manufactured from a renewable resource. You aren't just consuming something like sunlight is a good source, some other renewable things, right? So, and you don't want it to compete. So PHB, if you're fermenting sugar to make PHB, and the sugar comes from corn or from soybeans or whatever, then there's a direct competition with food, and the same with polylactic PLA, polylactic acid. So you could be competing with food production. I mean, when that happens, then all of a sudden you have a whole other group of people protesting your operation, right? So basically it's a political issue. It's also starvation, but right. Tunable properties. So like you saw from the Lyondell people, so they spent a lot of time designing polymers different needs, like oxygen permeability or water vapor permeability, keeping germs out, right? Also like not degrading in UV. So, and then having a good modulus for different parts that you make with it. Crack resistance is a big deal. And then the temperature use range. So that's kind of an issue with PHB because it's got a glass transition at 4C. So that means in a normal winter in Cincinnati, your kind of flexible polyethylene-like material will turn into a glass. And that means that it's probably not going to have the properties that you want it to have. Right? I mean, 4 degrees C isn't that bad. So PLA has a glass transition of 50 C. So the normal operation is as a glass, and if you get kind of a warm day and it's on your dashboard, it's going to turn into a puddle. So it's kind of like these temperature ranges of operation. So the glass transition temperature for polyolefins is like minus 100 C. So you'll never see it, not unless you're dead, right? So basically, it's a perfect material, and the crystallization melting is like 110 or 120, so well above boiling of water. So you have materials that are perfect, like we've naturally endowed with these materials that are really exactly perfect temperature range for our use, how we want to put them to use. And these biomaterials don't exactly fit into that perfectly. So somehow, right, so you can tune this, especially with the polyhydroxyalkanates like PHB, you can put in copolymers that tune the properties. So you can do butyrate, valerate. So it's got a methyl and an ethyl group, and that tunes the crystallinity. It kind of changes the TG and the TM. So it's possible, at least with PHB, to tune it somewhat, depending on, and you can genetically engineer microorganisms to grow copolymers, believe it or not. So they've done this. And and also depending on what you feed it. So if you feed it soybean or if you feed it glucose, it makes different PHB for some reason. I'm not sure they understand why, but basically what you feed it affects the price of it and also affects the properties. So there's some tunability even with those two polymers that, well, with PHB, where you could kind of mess around with this. PLA has a tunability that it's a stereo isomer. So there's two stereoisomers, like there's a right-handed one and a left-handed one. And how much of right-handed and left-handed you put in changes the TG by like 50 degrees or something, I think. So there's some tunability in PLA too, in that sense. And then a big part of this is that, so you saw from Amit, Kulkarni from Avian, that the whole, there's a chain of a value chain that goes into making a plastic thing, like a shampoo bottle. So it starts with the company making the plastic, and then it's going to go to like a compounding place like Avian, and then it's going to go to a company that's going to make the thing, like an extruder company or a film blowing company. And then it can go to a third company that's going to like stretch the film to change the permeability properties or do something else to the thing, put a label on it. And then it's going to go to a company that's going to fill it. Then it goes to the marketing company like P&G is going to sell it. Right. So there's like maybe 6 companies involved in it. And if you throw in like, oh, let's use PLA instead of polyethylene, every one of those companies is going to blow up. Like they're going to go nuts because they've invested. So some of them are small operations. And then they've invested like 10 million bucks in these blow molding machines. Like each mold in a blow molding costs like $10,000-$15,000. So if they have to get a different mold to use PLA instead of PE, it's a significant number on their budget sheet, right? So these people are really sensitive to any changes in what you feed them, right? They're like go nuts about it because if it jams up, like they're not making any money and they run 24 hours a day. It's like when they shut down because the thing jams because you stuck a PLA into it, you can't even do a test run. Like there's no possibility of even doing a test run on their equipment because they don't want you to touch anything. Like they're living on just the faith of God keeps the thing going, So basically And they aren't this small margins that they're making. It isn't like they're making a huge profit. I mean, they make a lot of money, but it's a small margin on each item, like cents, you know, so it's basically, anyway, that kind of operation, they're really sensitive. So talking about interchangeability of a biomaterial for this is a huge part of the whole thing. This will kill the whole operation. Like if you can't just plug and play your stuff with polyethylene, then it's never going to happen. Like they'll never do it. Not unless you make it illegal to do polyethylene or something like that. Even then they won't do it. Like they'd rather go to jail than change their polymer. You know, so anyway, so that's a pretty big issue. And what kind of additives do you have to have? Do the additives you have work? Are the additives you have toxic and biodegradable, or do they exist to add to this stuff? So the whole additive package, like the stuff Avient does, and what Sun does, you know, is going to have to change to match these other polymers. So it's like, it isn't just, again, it's like a plug and play issue, right? So there's a lot of issues with introducing a new plastic into the field. Let's see, I'm gonna kind of do that, I guess. There, so, all right, so this is kind of, this is just an overview of the 4 zones here, like the fossil fuel, which is in the bottom. I think it was number 1 at the bottom before, but here it's up here. But basically, everybody has this 4 thing, like every paper has the same thing. But anyway, so these are the non-biodegradable fossil fuel plastics, like main ones, like PVC, polystyrene, PET, polyethylene, polypropylene. And then, so these are durable, non-biodegradable, resistant to hydrolysis. It's like, that's a thing, like polyvinyl alcohol is hydrophilic. Like you can use it to make something like nylon for fabrics and things, and it's biodegradable, but comes from fossil fuel. So the gray is fossil fuel, but it's hydrophilic too. Nylon's hydrophilic, but this will dissolve in water, you know, so that's kind of a problem. The PBAT, I don't think is a, this polybutylene, let's see, polybutylene, so there's a 4, 1, 2, 3, 4. Terephthalic acid is here. So it's polybutylene AT. It's not a popular polymer. Polybutylene adipate coterephthalate. Oh, the adipate is over here. I see. This is butylene. Adipate is this. It's like a dicarboxylic acid, and then it reacts with the diol, 2 alcohols. Then it condenses water off, and then you make this ester bond, right? And this is a terephthalic acid with a butylene. So this will break. So this part of it will biodegrade the butylene part. So then you're left with terephthalic acid, and this suck in away. Is it adipate, adipic acid, I guess. It's also succinic acid. This is succinic acid, that's adipic acid. Right? So it's a diacid. Anyway, so those will be the reaction byproducts, and this makes like ethanol or butanol or something, right? So it's kind of like less toxic. So this aromatic thing is great for you. That one's probably not good. And then these things are probably okay. So anyway, it breaks up the chain by biodegradation on that part. And then PBS is polybutylene succinate. So it's the same as the adipate, except it's got 2 carbons instead of 4. And the diacid. Anyway, they're all those are condensation polymers, and this is the free radical polymerization for PVA. So this is like the same, these are all free radical, except for PET is a condensation. So water comes off. You have the ethylene glycol and the terephthalic acid makes PET. Water comes off. These are just vinyls that opened up and just make chains. And the PVA is a vinyl that opens up, makes a chain. These are all condensation polymers, right? So anyway, so those are commercial. These will biodegrade and these won't. And then these are the biopolymers, like these are the bio-based polymers. So if you can make polyethylene from ethanol, you can make polypropylene from ethanol, you can make polycarbonate from ethanol, you make polyurethane from some other biosource. PET, the ethylene glycol, comes from ethanol, and the T terephthalic acid comes from oil. And then this both come from some kind of fermentation process. This is furanoate, PEF. That's one, polyethylene furanoate. Right, so the ethylene is that part, the ethylene glycol, and the furanic acid. It's this thing with a oxygen in it. So anyway, so those are biodegradable, but coming from so bio-based, non-degradable. And then these are bio-based and degradable. So PLA and polyhydroxyalkanate. So the R group here, so this is PHB with a methyl sticking out. If it's an ethyl, it's polyhydroxy valerate. And then there's a couple others. Right, so that you can put like 1 carbon, 2 carbon, 3 carbon, I think. Butyrate's 1, valerate's 2, and then there's a couple others. You can make, and you can design bacteria or bacteria to grow these with different copolymer compositions. He says M and N, so you have different copolymers in this thing. Then you have cellulose and starch. So they look kind of the same, but they're different because the oxygen, see the oxygen goes down here and the oxygen goes up there. So they're the same thing, except they have a different beta, 1,4 beta bonding. So 1 is here, 2, 3, 4 is there. And you can also have a 1, 2, so you can bond here. So you can have a 1, 2 and 1, 4 bonded, which would make a branched, like a hemicellulose. So it would branch off, right? Anyway, the base unit of this is glucose, that thing right there. Like if you just put an OH here instead of an ether, then you get glucose, and glucose you can eat, and so can bacteria. So if you break these things down into glucose, then you can make ethanol, and from ethanol you can make PE and PP. You can make the ethylene glycol part of PET. So basically, cellulose is possible to start with. Easier to start with is starch because it's easier to digest, and also cellulose bonds better, so it's harder to attack that bond because it's like crystallized and stacked up, so it's hard to access that bond to break it apart. The starch is easier because it's not stacked in that way, and also there's more bacteria that eat starch than there are that eat cellulose. So basically, both of those can be used as feed to make, say, ethylene glycol, which could be used to make PE, PP, PET, half of it, and some of the others, right? So anyway, so there are, anyway, so that's kind of a picture of this. Bio-based, what's the goal? Mass balance, make plastics from agricultural waste, make monomers. This is generation 1 is going to be to make ethanol. And generation 2 is this fermentation of agricultural waste stuff. Gen 2, bio-based plastics, right? Then make monomer from fermentation and industrial polymerization, biodegradable by genetic selection. So this is the other thing, like you can compost in your backyard, you can compost in an industrial composter, so it's a higher temperature and high pressure, and then you can anaerobically compost, which produces methane. So normal composting makes CO2. Anaerobic composting in a reactor makes methane, and in like a landfill where you have it covered with no oxygen, and that methane can be used. It's one of the sources of methane that you can use through water shift gas reactions and field and I never remember that other reaction. There's a reaction you can make like alkanes from it, right? So methane you can turn into alkanes, and alkanes you can turn into ethylene or propylene or any of the other polymer groups. So basically, from methane, if you make methane, you can make any of the chemicals at some cost, with catalysts and et cetera, right? So it's possible to turn methane from biodegradable genetic engineered microbes or anaerobic composting back into polymers. And it's being done somewhat, but basically not on a huge level you know about it. Right? So then natural biodegradation, industrial biodegradation, so industrial composting. And then there's this issue that was around and still around that people say, like, you make polyethylene bag, and you put some starch into it. It's pretty simple. So you just add in 10% starch. And then you get a bag that you can call that biodegradable. I mean, they label that, sometimes they make those like green bags. It's just polyethylene with some starch in it. The starch gets eaten by bacteria easily. And then the bag kind of falls apart into really tiny pieces. In fact, into microplastics. So basically there's a lot of this kind of biodegradable plastic around that isn't necessarily great to have, because if you're worried about microplastics, you're just generating microplastics in that process. The little pieces of polyethylene that could be micron size and not like, or millimeter at least, are not going to degrade. So basically you've shredded the thing up into little pieces through a degradation process. So it makes it look kind of bio. Anyway, people buy that. So this shows, anyway, so this is this kind of slick graphic from this Nature paper. You can always tell a Nature graphic, right? So this is a life cycle of plastics. So you're going to start with oil and gas. The yellow is like fossil fuel, and the green is like bio, right? So they're both coming into this. So you're going to start with the same monomer. Like it could be the same monomer that you're getting from oil, or so it's ethylene, say, right? So you have like a bio-based plastic production is purple, and the gray is like fossil based. And you can mix the two, so you can get a mass balance on it. You get the monomer. You're going to polymerize it however you want, like high density, low density, linear low density, metallocene, whatever polymerization you want to do. Make the polymers, and then you're going to have to process the polymers into something, and then you make the product. So the normal route then is the linear economy, and it's going to go to like incineration or landfill. And then kind of a semicircular route is to go to mechanical recycling. In this paper, they see that as a dead end because make a low-grade product and it still ends up in landfill. So that's debatable. I mean, I think that's a little bit debatable, but that's how they show it, right? So this is a dead end linear process, and then eventually it ends up in the ocean, that's also a little bit questionable. There it is. Or it makes CH4 in an anaerobic, which is a greenhouse gas, right? So anyway, then if it's a green, then you can go like, so there's also from the fossil, you can take, so PET is already being recycled back into monomer, and it goes through this routine. That's possible. That's like, I think 10 or 20% of PET ends up on that route. So it has to be like the guy from Rumpke said, PET bottles are different PET than the blister pack things, those salad packs, and you can't be mixed. Only in Columbus will they collect the blister pack things, but the Cincinnati Reuse and Recycle Center will take them. Then they'll recycle the blister packs. They have to go to a separate plant. The bottles, there's a lot more of them, I guess, and there's already like Eastman and Tennessee takes those. They have a plant to take the bottles. I think they're taking the blister pack things too, but they have to be separated from each other. Anyway, so that exists, right? And then involving like some solvent catalyst, and the question is like the cost involved in that, but compared to just getting it from oil or you can also get the PET from, at least the ethylene glycol from the corn fermentation from ethanol. So anyway, so that's one. And then the other route is this pyrolysis, the thing that Lyondell's talking about, their magic pyrolysis thing. It's going to give you monomer. It gives you basically oil again, and then you have to refine that and get to monomers. Right, so you're going to get some kind of tarry oil thing from it if you cook plastic waste, basically any kind of plastic waste in a pyrolysis unit. So those are the yellow parts, and then the green parts are functional backbone. So you can gene edit microorganisms that'll eat this stuff and make monomers. So it's possible to do this routine. I mean, these things exist, but this whole operation on an industrial scale doesn't exist, right? So this is the PEF you don't see much. And then there's anaerobic, which makes methane, and aerobic, which makes CO2 composting of the bioplastics. So this, again, that can be industrial or backyard, right? And then methane, they show going to burning to make energy, but actually the methane can be reworked into, chemically reworked into plastics again. So methane's a good thing to start with. I'll show you the process of doing that. You might have already seen that kind of thing. The Fischer-Tropsch reaction. You can take methane and turn it into alkanes, right? In other words, you can basically make it into ethylene. So this is the deal. Like, so you have so you're gonna make like precursors from something like well, if you can break down wood enzymatically into sugar, which you can do, and then you can use the sugar, you can ferment the sugar into these products. So it's possible to take glucose or glucose fructose and then ferment it into bioethanol is the most popular thing. The bioethanol can be used to make ethylene or ethylene glycol for PET, and the terephthalic comes from the oil, the black thing. And then you can also take it and ferment it into these kind of more odd things, HMF, furan, I guess it's a furan compound into a diacid, furano-dicarboxylic acid. And then that can be made into something like PET, this PEF, which is not, I think this is not biodegradable. So basically, anyway, it's a complicated routine here. And then it's possible to take sugar, ferment it into the glycols, I guess, and mix it with an isocyanate from oil and make polyurethane, which would be a biopolyurethane, quote unquote. And then polycarbonates from bisphenol A. This is like the Bhopal chemicals. And then vinyl chloride to PVC and styrene. These are from oil, right? So then this side has so you can make cellulose acetate polymers. Would be a plastic that you can make from just directly from cellulose by chemical treatment. And you can take the sugars and ferment it directly to polyhydroxyalkanates, or you can ferment it to lactide, which you can polymerize to PLA. So PLA has like a two-step. This is a one-step from fermentation. So the two-step has more control over what you make, molecular weight and also like the purity and things. Or do you have to separate the plastic from parts of the microbe that made it? In this case, you have just the lactide and it makes polymer. Then you can ferment and make succinic acid to make this PBS, polybutylene succin-08. Right, there's 4 here, so it's a butylene diol with the carboxylic. And then you can also make these copolymers that are biodegradable with mixing with a petrochemical adipic acid, and polyvinyl alcohol comes from oil directly. So it's not a biosource. Anyway, so that's kind of there's a refining operation going on here, I guess. So the refineries here are breaking down into the monomers and into the polymers. Anyway, so bottom line is the price of the stuff. So it's basically PLA $2 to $3 a kilogram. The hydroxyalkanates like $5 to $6 a kilogram, and then polyethylene is going to be like on the dollar range. Right, so it's 2 to 5 times more expensive to do a biopolymer compared to the commercial polymers, to fossil polymers. So there's a price tag to it. And then bio-PE is about the same price. And then these other polymers are higher priced, right? So polyvinyl alcohol exists and it's about the same price as polyolefins, but it's a fossil-based polymer that's degradable, right? So right, it's possible to mess around with these things. So if you they also like tag out like global warming and acidification, which is like acid rain from the processes. Somehow they go through the entire processes in this paper. So anyway, so the global warming potential of PHB on this scale can be negative. So it can consume CO2, or it can be 4. And if it's 4, it's higher global warming potential than any of the polyolefins by a factor of 2. But it costs more and it's worse for the environment, right? Or it could be better. I mean, it depends on how you make it. PLA is like 2, so it's a little bit worse than the polyolefins for global warming, right? So you kind of have to consider, you think it's a good thing to go biopolymer. Well, it's good for recycling, but it's not necessarily good for the environment. And acidification, these are like higher numbers, right? 75 and then 25 versus, well, for some reason, low density polyethylene is higher than the others, but anyway, they're comparable in terms of that metric. So I don't know why they included that. And then the time of biodegradation, not never degrades. And then these things are like a couple months. So there's a balancing act between what, basically what parameter you want to pick to say what's the most important thing, like for bioplastics, like what are you going to do in this thing? It's not such a clear-cut thing that these green things are better. I mean, they could be better, but it depends on how you look at it. This is just the labeling thing, which is a mess. So you can't tell. I mean, unless you're in Austria, maybe you could tell, but basically it's difficult to tell like what you can put in what bin, for what's going to go into your compost bin and what's going to go in the recycle bin. There isn't a consistent labeling for any of this stuff. So basically you're left without any kind of direction when you have some kind of waste that you want to put somewhere. You don't know where to put it. This is just kind of a list of all the possible, and then the blue things are visible to people, to consumers, and the black are kind of behind the scenes, right? So you have the things you already have, like the manufacturing exists, cost is already low. People have designed it to be what you want. They last a long time and they do what you want them to do. But there's this waste problem. They don't mention that. So the sustainable is some properties, functionality, same, some of them have the same, can have the same. So the engineering of that's been done. People have already figured out how to make any kind of like PLA or PHB, you can make any kind of product with it. Films, barrier films, injection molded parts. They're all basically equivalent to polyethylene. I mean, that has, part of that was done by Procter and Gamble. Like they did the entire process to make a PHB based diaper. It's like almost all the diaper except the super absorbent is plastic, polyolefins. And they made diapers on a commercial scale out of PHB, like the whole thing. Like a part you think is fabric when you feel it is polypropylene film that has had small holes blown in it, that are the holes of the size of your fingerprint, so it makes it feel like it's textured like fabric, but it isn't. It's all polyethylene and polypropylene. So the whole thing is just, so basically they can make those with PHB for about the same cost, but they don't. They didn't, so basically, anyway, it's possible to get the same functionality. They're theoretically more environmentally friendly, but like PLA is kind of a lie, and PHB, maybe it's a little bit of a lie. All right, they also, Procter and Gamble also did studies of like, if you want to tune the properties by putting valerate instead of butyrate into the PHB polymer. But then they did studies and they found out like if you do these copolymers, some of them don't really biodegrade. Right. So once you start tuning the properties to match up with polyethylene, polypropylene, then you find out you're losing out on the degradability. So the whole thing kind of falls apart. Right. So the more tuning you do to it, the less environmentally friendly it is. Right. And then the cost is 3 times as much, I guess. But again, like the plastic cost, so I don't even know what diapers cost now. I did it one time, but basically I think the cost for the plastic that goes into it is like maybe maximum 5%. So if you triple that, I don't think it matters much. I think the super absorbents probably cost a lot more than the plastic parts that went into it. So I think the cost doesn't matter. I think the idea of like tripling the cost of the polymer doesn't make any difference. It's more like the processing, how you'd implement it in the processing streams they have. Anyway, then this idea of like design for recycling doesn't exactly exist now, right? I mean, there was multi-layer films, and then even just how you break it apart. If you have multiple plastics, like a cap is different than the bottle, how do those separate in the recycle stream so you don't get mixed plastics in it? Like, so this design for recycling, there isn't much appetite for it and it doesn't seem to really exist much. There's some examples, but oh, the homework on the sneakers was really good. Like some people like gave some links that were really nice. So there are places where you can buy recyclable or sneakers that can be, they're designed to be reused, you know. There's one company, I forget, I put it on the webpage. But anyway, that was a pretty good homework. I got two groups, I think, gave some pretty good answers to that. Like I gave them a couple extra points, but anyway, so there is design for recycling, but it isn't, there's not much of it, you know. And then let's see. So yeah, so there's all these issues: transportation, carbon emission, processing, uh, functionality, price, and then end of life. So stage 4 emissions from anaerobic composting, and then anyway, so that's kind of the loop. So then laid on top of that are like how you want to control it. Like if you want to affect this so that you have bioplastics involved in the consumer products, then you want to have like regulations, so bans or whatever, extended producer responsibility, quotas for recycling, mass balance economics. Or do you want to have incentives like somehow give people a bonus if they use recycled things? I guess those are the only two things they consider here. They should probably consider litigation, like if you sue the company because they destroyed the earth, you know, that would probably have more impact. Like Ahmet didn't even seem to understand that like they could get sued, right? So I think the litigation part is probably a lot more, especially in the current environment, than either of these regulation things. Because except for locally, like these aren't going to happen, but the litigation probably will take off. Like, and it already, what was that I read about? Oh, Shell Oil, right? They were sued for global footprint in the Netherlands. And it made it, they lost the case, and the case answer was that they had by 2030 to cut their new sourcing of oil by 80%. Like, so they appealed it and they won the appeal like yesterday. Right. So there's this litigation even in Europe is going on. So I think that probably litigation is the best, if you want to affect change in this, like litigation is a way to wake people up. And the reason that the judge said that they didn't approve the appeal, or said they reversed the decision, is that there's affecting Shell, some other company would come in and like just provide the oil. Like, so making Shell cut their operations wouldn't really impact the result, which is kind of a bogus thing. I mean, it makes sense on a certain level, but actually, if other companies saw that they were going to be litigated and lose, like there's a capital investment to going into producing oil. So like they're not going to, and somebody has to invest it, like Citibank, I guess, is the main investor. Not that I read this stuff. So basically, Citibank isn't going to give them money if they think there's going to be a litigation in the Netherlands that'll shut them down. Then there's a huge loss. So basically, it's not true that someone else is going to replace them because they're going to see the litigation, the previous litigation, though they're doing exactly the same thing. They're not going to do it. Right. So litigation probably is the most effective thing, even though people don't like lawyers, but basically they may save the world. You know, it's possible. Anyway, so let's see. So this is the table that shows like, so PHB, so this is the glass transition, 10 degrees C. So that's kind of bad. Like if it's going to turn, so you have a flexible diaper made out of PHB, you take your kid out and it's like 10 below zero outside or something, then basically the diaper is going to turn into glass and shatter. that's not really good, right? I mean, once you warm it up to body temperature, it'll be flexible again, but it's like a mess. So that's kind of a bad feature of PHB. I think they don't give the other copolymers here, so they have different glass transition temperatures. Then the melting's okay. It's like even higher than the polyolefins, like 165. The PLA though, let's see. PLA's got a glass transition at 50 to 60, so it's normally glassy when you have it. Well, let's see, they give a degree of crystallinity. So it's 10% crystalline or 3%. These are the two different stereochemical, like left and right stereoisomers. And then basically they have different, same glass transition, but the one's amorphous, one's crystalline. So one's slightly crystalline, 10%. So anyway, depending on how you make it, right? So it's like PET, they say it's crystalline, but basically when a water bottle's amorphous because you quench it fast enough, it doesn't, there's a kinetics issue with the crystallization. So it can't crystallize in time. So, and it's got a high melting point. So it's kind of the maximum crystallization temperature is like 50 degrees below that. So 210 C. So you never reach that in the normal conditions unless you put a solvent into it, and it'll crystallize right away. But so anyway, so there's like different issues involved with these operating temperatures for these. You can see like the polyolefins is such a low glass transition, you never reach it. So basically these are amorphous with crystallinity holding it together, like 50% crystalline, 650 to 80. So anyway, so they kind of stack up these two candidates, the PHB and the PLA, but there's certain problems, like particularly the TG for PHB isn't great. That just shows how the bugs eat the sugar to make PHB, which I can't understand exactly. There's a lot of enzymes involved, some kind of NADH to NAD plus, which I think is an energy thing or something, but ATP is definitely energy. But anyway, so that's kind of a biochemical look at it. And this is supposedly like a reactor scheme of how you can do it with different operations, like stage polymerization, batch polymerization, continuous flow reactor. So same as chemical engineering. It's just kind of like biochemical engineering, like various operations. I don't see any recycle loop, but basically it's probably a recycled operation too. And so it's just there's different ways to make, and then depending on what you feed it. So for this is PHB again, so you're directly making the plastic from sugar, from whatever. So you have glucose, fructose, and soy cake are the ones they looked at. You can basically make it from almost anything, right? So, and you can genetically engineer bacteria to make it. So basically it makes it under stress. Like plastic isn't a natural thing for a bacteria. When it's stressed and it tries to store food, it stores it as plastic, and then it can consume the plastic when it needs it. So basically you take the bacteria, then you have to get it growing happily, and then you stress it, like you starve it. So then it's going to want to make plastic to store energy. It's like people make fat in the winter or something, or bears do at least. But so it's that kind of idea. So anyway, so you want to put it into winter bear hibernation mode so that it makes the stuff. So people have studied it. They know how to do it. And that basically feeding it different things surprisingly gives like pretty broad range of properties. Like even the glass transition is different, and the melting point is different, and the degree of crystallinity is different. So depending on how you make it, so you can this is probably happy land for intellectual property people, because you can pick, oh, only if you feed it soy cake under these conditions will you make the super plastic that's better than all the other ones. And there's probably an infinite number of those conditions that you could patent. Maybe one of them is of some value, right? So it's basically anyway, that's kind of the scheme of like, you could get IP from this pretty easily by messing around with it. I think P&G had a huge amount of IP on making PHB, which they gave to the Kanaka Japanese company that makes PHB. Like they sold it to them with the people that developed it. They sold the people and the patents like one day. Yeah, they sold the group. Yeah, that's what they did. It's pretty weird. Like, it's pretty weird. Like, these people are like 20, 30 years at the company, ready to retire, and then they sell the IP and the people and everything, out from under them. I mean, they made out, like, everyone that works at P&G ends up like a millionaire because of this, because of the stock option thing. I mean, even the technicians. I mean, even I know technicians that work there. I mean, they worked for like 25, maybe 30 years, but they're, when they finished, they had like 2, 3 million bucks in stock. I think yeah, this one guy I'm thinking of, he was just I don't know what band it was, but basically seemed like a pretty good deal. I mean, he was a smart guy. He was really good, definitely like great, super at his job, because I worked with him a little bit, but basically, I think he retired like 60 or whatever, maybe less than that, like 50 something. And he didn't need to work anymore because he was just living off the P&G stock. So they do well there. I mean, it's good. I mean, I think everyone does pretty much, It's ranked like the top place to work. I mean, like, so, I mean, they give like maternity leave and everything, so.
Yeah, you don't give paternity. So like,
Yeah, paternity too, yeah. Yeah, so it's pretty sweet. I mean, it's a little bit, you have to live with the psychology of it, because it's marketing. I mean,
and my mom worked at, like, I grew up with like mom who was like the embodiment, and like I kind of just like always wanted to be her, so I like
yeah,
developed, like, the emotions I guess that I needed to
yeah.
like fit in.
Mhm.
But if you like don't like the culture, then like it's definitely. But I will say that like when you get to like band 3, which is like you're like managing like a team for like different projects, then like you're working over 40 hours.
I mean, like, I knew a guy who worked at Exxon, like they force him to buy Exxon gas, like he can only buy Exxon gas stations. I was driving with him somewhere. It's like, oh no, I can't go there. It's like, we need gas. No, we got to go to the Exxon stations. P&G's a little bit like that. I mean, there's some kind of brainwashing thing going on. Right?
Because like what a bigger version, I don't know, I feel like Charmin is so much nicer than whatever the heck they put in the UC bathrooms, but like.
I mean, it's probably true. I know, like, I like their toothpaste, but
Yeah.
basically, anyway, there's an issue with that though. I mean, the benefits and everything are great. Also, they're like they had the plant in Ivorydale, right? So they like fired everyone down there. They shut it down. They sold it to the St. Bernard Soap Company. But then there's still part of it they owned. And like the security guards and stuff there, they were like hired to some other company. So they didn't know about like the dangers and things about the plant. You know what I mean? So they have a little short-sighted, and like in the past, like everyone was part of the family, like everyone that worked there. And then they started getting this idea like, oh, we could farm that out to like whatever. And then like no one's part of the family anymore. So there's no history, like it changes too much. So nobody knows like what happened at the place before and like why you don't walk over there, things like that. So that they've lost this kind of, anyway, but still, like if you're in the family part of it, it's great still. But I think the contractor part isn't that great. And I think all the companies are doing that, not just P&G.
Which don't get, have a job for 6 months and then like you're gone. Like there's like very rarely ever that they would retire a contractor for like another 6 month period.
Yeah, and it's some important people. I mean, the security people definitely. So that's a little bit short-sighted, I think. Because sometimes say there's a fire, like you need to trust somebody. Like the people that are going to respond, those are important people. I mean, they might not be making the diapers or whatever, but basically you rely on them in a certain circumstance, and it'd be good to have somebody that's like in the family, not someone that's just a contractor for 6 months there.
I think they keep the security guards around, but like the science contractors around.
Yeah,
I've seen the same security guard at my site for like the past 3 years.
yeah. Anyway, those are the gripes I have about P&G. Otherwise, it's a great company, I think. Yeah. It's good stock, like whatever they're doing is working. I mean, It's like in terms of the investor end of it, but anyway, so I'm not sure how that happened, but so, yeah, why don't yeah, well, this is just PHB, like so the price of the PHB, like if you use Cheeseway, it's pretty cheap. All right, so 50 cents per kilogram, and that other table. Let me just go back for a second. So this says per kilogram, $3 to $5, and then this thing says 50 cents or 7 cents. So this would be way less than any polyolefin. So it depends what so this is waste substrate, but still. Oh, I see, production costs, that's substrate cost, production costs 22 cents, so still 22 cents puts it like pretty, like more cheaper than polyethylene. Wherever that other table went, 22 cents, it's like $2 for polyethylene, if you can make it for 22 cents on Cheeseway. But again, there's like a limited supply of Cheeseway waste substrate. So that's the price if you want one truckload, but if you want to supply the entire economy for tons, maybe there's not tons of Cheeseway waste-based substrate. Anyway, so there are different ways to get around the cost, I mean, I guess, on this. Anyway, so this is companies. So next time I'll just go through some of the companies and continue on. This is the company that bought P&G's thing, this Kaneka. They're in like Mississippi or something. They have a plant, but it's Japanese, sort of like worldwide. I'll go through a little bit of them, but I think we're out of time. I don't want to only go an hour, so why don't I quit there and then can start up on Thursday. Hopefully I can get through all this stuff, but anyway.